Hello everyone, welcome to this YouTube channel MathSense. This is the fourth lecture of this particular series. In this lecture, we are going to discuss about linear programming problem, basically model formation. This is a fourth lecture of unit 1. So let's begin with the first term, that is general mathematical model of linear programming problem. So here we are describing general mathematical model. So the general linear programming problem or model with n decision variables and m constraint can be stated in the following form. Optimize maximum or minimum z is equal to c1x1 plus c2x2 plus so on plus cnxn subject to the linear constraints a11x1 plus a12x2 plus so on plus a1nxn in a bracket less or equal to greater or equal to bracket over b1. So here we have three different terms, two inequalities, less or equal to, greater than or equal to, and one equality that is equal to. Same for the next constraint, that is a21x1 plus a22x2 plus so on, and last term is plus a2n xn in a bracket less or equal to, greater or equal to, and b2. Continuing in this way, the last constraint is am1 x1 plus am2 x2 plus so on plus amn xn in a bracket less or equal to, or greater than or equal to bracket over bm, and x1 x2 up to xn which are all greater or equal to 0. So in previous lecture we discussed about the structure of linear programming model. So in that structure we have decision variables. So here x1 x2 up to xn are decision variables. We have objective function, and this is our objective function. Here we have constraint, so these are all constraints, and last one is non-negativity condition. So this is non-negativity condition, where the function z is the objective function, x1 x2 up to xn are the decision variables. The expression less or equal to, or greater or equal to means that each constraint may take any one of the three signs. Cj, where j running from 1 to up to n, represent the per unit cost or profit to the jth variable, and bi, where I running from 1 to up to m, is the requirement or availability of the ith constraint. x1 x2 up to xn, which is all greater or equal to 0, is the set of non-negative restriction on the LPP. In real life problems, negative decision variable have no valid meaning. In this module, we shall only discuss cases in which the constraints are strictly inequalities, either it is less or equal to or greater or equal to. Usually equal to is equal to cases are rare. In formulating the LPP as mathematical model, we shall follow the following 4 steps. So now onwards we are going to present different steps. So first step to formulate LP model is identify the decision variable and assign symbols to them. Those symbols are x, y, z, or you can assign x1, x2, x3 and so on. These decision variables are those quantities whose values we wish to determine. The second step is identify the set of constraints and express them in terms of inequalities involving the decision variables. The third step is identify the objective function and express it in terms of the decision variables. And fourth one is add the non-negativity condition. For a problem to be a linear programming problem, the decision variables, objective functions, and constraint all have to be linear function. Now, formulation of linear programming problem. So here we have first an introductory example 1. So this is the problem statement, or we can say this is our example. So which states that a company makes two products, say capital P and capital Q, using two machines, say capital A and B. Each unit of P that is produced requires 50 minutes processing time on machine A and 30 minutes processing time on machine B. Each unit of Q that is produced requires 24 minutes processing time on machine A and 33 minutes processing time on machine B. Machine A is going to be available for 40 hours and machine B is available for 35 hours. The profit per unit of P is rupees 25 and the profit per unit of Q is rupees 30. Company policy is to determine the production quantity of each product in such a way as to maximize the total profit, given that the available resources should not be exceeded. So here our task is, the aim is to formulate the problem of deciding how much of each product to make in the current week as an LP. So the first step is defining the decision variable. We often start with identifying decision variable. That is what we want to determine among those things which are under our control. Here the company wants to determine the optimal product to make in the current week. So there are two decision variables. So here we denote two decision variables with notation x and y. So x is the number of units of P and y is the number of units of Q. Now next step is choosing an objective function. In description, this one is the third step, but you can alternate those, step number 2 and step number 3. So here we first choose an objective function. We usually seek a criterion or measure to compare alternative solution. This yields the objective function. We want to maximize the total profit. The profit per each unit of product capital P is rupees 25 and profit per each unit of product Q is rupees 30. Therefore, the total profit is 25x plus 30y. If we produce x units of P and y units of Q, this leads to the following objective function, and that is maximum of 25x plus 30y. Now here you can see this one is a linear function. So here we noted that the objective function is linear in terms of decision variable x and y. That is, it is of the form ax plus by, where capital where cap A and B are constants, and we typically use the variable capital Z to denote the value of the objective function. So the objective function can be stated as maximum of Z, and that equal to actually 25x plus 30y. Now here third step is identifying the constraints. So in many practical problems there are limitations such as resources, physical, strategic, economical that restrict our decision. We describe this limitation using mathematical constraint. Here, the amount of time that machine capital A is available restricts the quantities to be manufactured. If we produce x units of capital P and y units of capital Q, machine A should be used for 50x plus 24y minutes. Since each unit of capital P requires 50 minutes processing time on machine A and each unit of capital Q requires 24 minutes processing time on machine capital A. On the other hand, machine A is available for 40 hours or equivalently for 2400 minutes. This impose the following constraint. Here, this data is given in minutes and this data is given in hours. So we need to convert that. So 40 hours equals to actually 2400 minutes. So that's why the first constraint for machine A, that is 50x plus 24y, which is less or equal to 2400. Now we same applies for machine B. Similarly, the amount of time that machine capital B is available imposes the following constraint. Then that is 30x plus 33y, which is less or equal to 2100. So actually here you can observe 30-minute processing time on machine B for unit P and 33-minute processing time on machine B for unit of Q, and machine B is available for 35 hours. So when we convert 35 hours into minutes, we get 2100 minutes, and that's why the second constraint is 30x plus 33y, which is less or equal to 2100. So this is our second constraint, 30x plus 33y, which is less or equal to 2100. These constraints are linear inequalities, since in each constraint the left hand side of the inequality sign is a linear function in terms of the decision variable x and y. The right hand side is constant. Now the last step is add the non-negativity condition. So here, in most problems, the decision variables are required to be non-negative, and this should be explicitly included in the formulation. This is the case here, so you need to include the following two non-negativity constraints as well. So x greater or equal to 0 and y greater or equal to 0. So the constraint we are subject to are 50x plus 24y, which is less or equal to 2400 for machine A time, and 30x plus 33y, which is less or equal to 2100 for machine B time. X greater or equal to 0, y greater or equal to 0. So these all things is just for understanding. So when we formulate LP model, you can directly write max z that equal to 25x plus 30y, subject to the constraint 50x plus 24y, which is less or equal to 2400 machine A time. Same for the next, that is 30x plus 33y, which is less or equal to 2100 machine B time. Here x greater or equal to 0, y greater or equal to 0. So here in the structure of LP model, you can observe this is objective function, x and y are decision variable, these two are constraints, and these two represent non-negativity condition. So this is the LP model for given problem. Now let's take a look on the next example. So here in the next example, problem statement is: consider a chocolate manufacturing company that produces only two types of chocolate, chocolate A and chocolate B. Both the chocolates require milk and choco only. To manufacture each unit of capital A and B, the following quantities are required. Each unit of A requires 1 unit of milk and 3 units of choco. Each unit of B requires 1 unit of milk and 2 units of choco. The company kitchen has a total of 5 units of milk and 12 units of choco. On each sale, the company makes a profit of rupees 6 per unit A sold and rupees 5 per unit be sold. Now the company wishes to maximize its profit. So here company wants to maximize its profit. How many units of A and B should it produce respectively? So this is actually a complete problem. But here we are just going to formulate LP model. We will discuss the solution process in next session. So here solution is, the first thing is to be represent the problem in a tabular form for better understanding. Yes, here we use better understanding. Actually, we put all those data in one table, so we cannot mm, we cannot forget any detail. So here, milk, choco, profit per unit. For chocolate A, 1 unit of milk, 3 unit of choco, and profit gain is rupees 6 per unit. For chocolate B, 1 unit of milk, 2 unit of choco, and profit gain is rupees 5. And total, now here we have number 5. This is not total of this 2 unit. Actually, that company kitchen has only 5 unit of milk, total 5 unit of milk, and company kitchen has 12 unit of choco. So let's decide decision variable. So let the total number of units produced by A be capital X, and same let the total number of units produced by capital B be capital Y. Now the total profit is represented by capital Z. So X and Y are decision variables and Z is objective function. So the total profit the company makes is given by the total number of units of A and B produced multiplied by its per unit profit of rupees 6 and rupees 5 respectively. So profit, so which is actually maximum of Z, that equals to 6x plus 5y, which means we have to maximize Z here. Now the company will try to produce as many units of capital A and B to maximize the profit, but the resources milk and choco are available in a limited amount. So those are the constraint actually. So as per the above table, each unit of A and B requires 1 unit of milk. The total amount of milk available is 5 units. To represent this mathematically, we have x plus y, which is less or equal to 5. Also, each unit of A and B requires 3 units and 2 units of choco respectively. The total amount of choco available is 12 units. To represent this mathematically, we have 3x plus 2y, which is less or equal to 12. Also, the values of A can only be integers. So we have two more constraints, x greater or equal to 0 and y greater or equals to 0. And you all know that the values of units of A can only be integers, so same applies to value of unit of B. So that's why x equals to 0 and same applies for y greater or equals to 0. For the company to make maximum profit, the above inequalities have to be satisfied. This is called formulating a real world problem into mathematical model. So first is maximum of z, that equals to 6x plus 5y. So this is objective function. This 2 are x plus y less or equal to 5, 3x plus 2y less or equal to 12. This 2 are constraint, and x greater or equal to 0 and y greater or equal to 0. These 2 are non-negativity condition. Now we have more example of LP model formulation. So the first one is, a manufacturing company is engaged in producing 3 types of product, capital A, capital B and capital C. The production department produces each day, components sufficient to make 50 units of A, 25 units of B, and 30 units of C. The management is confronted with the problem of optimizing the daily production of the products in the assembly department, where only 100 man hours are available daily for assembling the products. The following additional information is available. So these are additional information here. So type of product, profit contribution per unit of product in rupees, assembly time per product, which is in hours. So for product A, the profit contribution is 12 and the assembly time is 0.8. For product B, the profit contribution is 20 and assembly time is 1.7. For product C, profit contribution is 45 and assembly time is 2.5. The company has a daily order commitment for 20 units of product A and a total of 15 units of product B and C. Formulate this problem as an LP model so as to maximize the total profit. So here LP model formulation. Before starting that, let's put all those data in a tabular format. So the data of the problem is summarized as follows. Here we have resources, or we can say constraints. Here we have product types, and this one is last column represent total. So first one is product capacity in units. So for A it is 50, for B it is 25 units, and for C it is 30 units. Man hours per unit. So for A, which is 0.8 hours, for B, product B, which is 1.7 hours, for product C, it is 2.5 hours, and we have total 100 man hours per unit. Order commitment in units, that is for product A, it is 20, and product B and C, it is 15. And profit contribution, rupees per unit, is 12 for product A, 20 for product B, and 45 for product C. So here we have all information about the example. So let's decide the decision variables. So let x1 that equal to number of units of product A to be produced, and similarly x2 is equal to number of units of product B to be produced, and x3 is number of units of products C to be produced. So we need to maximize profit. So that's why capital Z is equal to, here profits is described in this format. So capital Z that equals to 12x1 plus 20x2 plus 45x3, subject to the constraint. So constraint about the labor means man hours, so which is actually 0.8 into x1 plus 1.7 into x2 plus 2.5 into x3, which is less or equal to 100. We have maximum that time. Now about material, so x1 which is less or equal to 50, x2 which is less or equal to 25, and x3 which is less or equal to 30. Here in table you can see the production capacity, and here we have manpower units. So by using this information, here we have two different constraints. And the next constraint is order commitment. So company the company has a daily order commitment of 20 units of product A and total 15 units of product B and C. So company should produce 20 units, minimum 20 units of product A and minimum 15 units of product B and C. So that's why The next one is x1 greater or equal to 20, x2 plus x3 greater or equal to 15. And you know that x1 is greater or equal to 0, x2 is greater or equal to 0, and x3 is greater or equal to 0. So this is the LP model for given example. Now the next example is a company has two plants, each of which produces and supplies two products, capital A and B. The plants can each work up to 16 hours a day. In plant 1, it takes 3 hours to prepare and pack 1000 gallons of A and 1 hour to prepare and pack 1 quintal of B. In plant 2, it takes 2 hours to prepare and pack 1000 gallons of A and 1.5 hours to prepare and pack a quintal of B. In plant 1, it cost rupees 15,000 to prepare and pack 1000 gallon of A and rupees 28,000 to prepare and pack a quintal of B, whereas in plant 2 this cost are 18,000 to prepare and pack 1000 gallon of A and rupees 26,000 to prepare and pack a quintal of B. The company is obliged to produce daily at least 10,000 gallons of A and 8 quintals of B. Formulate this problem as an LP model to find out as to how the company should organize its production so that the required amount of the two products can be obtained at the minimum cost. Here we need to minimize the production cost. So let's represent all those data in a tabular form. So for LP model formulation, the data of problem is summarized as follows. So here we have resources, or you can say constraint. Here we have products, so we have two products, A and B, and the last one is total availability in hours. So first we have preparation time in hours. So for product A and for product B. So for product A, in plant 1, 3 hours per 1000 gallon and 1 hours per quintal of product B. And plant 1 has 16 hours. Same for plant 2. Plant 2 has maximum 16 hours, and for product A, plant 2 has 2 hours per 1000 gallon and 1.5 hours per quintal. Minimum daily production is 10,000 gallon of product A and 8 quintals of product B. And the last one is cost of production. In plant 1, cost of product A is 15,000 per 1000 gallon and 28,000 per quintal of product B. In plant 2, for product A, we have 18,000 per 1000 gallons and 26,000 per quintal of product B. So these are the all informations. Now let's decide decision variables. So let x1 is equal to quantity of product A to be produced in plant 1, x2 is quantity of product A to be produced in plant 2. Here the quantity of product A is measured in 1000 gallons, so that's why we mention in 1000 gallon, and same for product B, it measured in quintals. So x3 is equal to quantity of product B to be produced in plant 1, x4 is quantity of product B to be produced in plant 2. So the LP model is maximize total cost. So capital Z is equal to 15,000 into x1 plus 18,000 into x2 plus 28,000 into x3 plus 26,000 into X4. So here you can see in the table. So we use this to form objective function. Now the constraints are subject to the constraints. So preparation time is 3x1 plus x3 for plant 1, which is less or equal to 16, and this one is for plant 2. So 2x2 plus 1.5 x4, which is less or equal to 16, and same for the minimum daily production requirement. So that is for product A, x1 plus x2, which is greater or equal to 10. We have 10,000 gallon, and same for product B, that is x3 plus x4, which is actually greater or equal to 8. And this is the non-negativity condition. X1, x2, x3, x4 all are greater or equal to 0. Now let's take a look on the example number 3. An electronic company produces 3 types of part for automatic washing machine. It purchases casting of the parts from local foundry and then finishes the part on drilling, shaping and polishing machine. The selling price of part A, B and C are rupees 8, rupees 10 and rupees 14 respectively. All parts made can be sold. Casting for parts A, B and C respectively cost rupees 5, rupees 6 and rupees 10. The shop possesses only one of each type of casting machine. Cost per hours to run each of the 3 machines are rupees 20 for drilling, rupees 30 for shaping and rupees 30 for polishing. The capacity parts per hours for each part on each machine are shown in the table. So those informations are mentioned here. So machine, drilling, shaping and polishing. And the capacity per hour is for part A, drilling 25 units, shaping 25 units and polishing 40 units. For part B, drilling 40 units, shaping 20 units and polishing 30 units. And for part C, drilling 25 units, shaping 20 units, polishing 40 units. The management of the shop wants to know how many parts of each type it should produce per hour in order to maximize profit for an hour's run. Formulate this problem as an LP model so as to maximize total profit to the company. So let's decide decision variable. So let x1 is number of type A parts to be produced per hour. X2 is number of type B parts to be produced per hour, and X3 is number of type C parts to be produced. So this example is quite different. So here we need to maximize profit. So first we need to find profit for type A, profit for type B and profit for type C. So since 25 type A parts per hours can be run on the drilling machine at a cost of rupees 20, then rupees 20 by 25, that is actually rupees 0.80 is the drilling cost per type A part. Similar reasoning for shaping and polishing. So here we calculate profit per type A part, and that equals to rupees 8 is a selling price, rupees 5 is a casting price, and we did another 3 different process, and that is drilling, shaping and polishing. So these are those cost, and finally we have 0.25. Same for the part B, profit per type B part, that equals to 10 rupees is a selling price, 6 rupees is a costing price, and this price is 20 rupees, total 20 rupees for drilling, and we are drilling 40 units of type B. Same for the shaping, total price of shaping is 30 rupees per hour, and we are shaping 20 units of part B, and here we have 30 rupees for polishing, and we are polishing 30 units of part B. So after simplification we have the final answer, or profit per type B part, that equals to 1, and same for the C. So profit per type C, that equals to 14 minus 10, that is selling cost minus costing cost minus the processing of drilling, shaping and polishing, and that equal to, after simplification we get 0.95. So using that we can write maximize total profit. We can write maximize total profit, capital Z is equal to 0.25 x1 plus 1 into x2 plus 0.95 x3, subject to the constraint. Now constraints are also interesting. On the drilling machine, on one type A part consume 1 by 25th of the available hour, a type B part consume 1 by 40th, and the type C part consume 1 by 25th of an hour. Thus, the drilling machine constraint is, so this is a time for producing x1 part, and this is the time for producing x2 part, and this is the time for this is the time for producing x1 unit of part A, this is the time for x2 unit for part B, and this is the time to produce x3 unit for part C. So x1 by 25 plus x2 by 40 plus x3 by 25, which is less or equal to 1. Similar other constraint can be established. So this is the first constraint. So this is, that constraint belongs to the drilling section. Now we have other three, that is for shaping and polishing. So here this one is our objective function. Now for drilling machine, x1 by 25 plus x2 by 40 plus x3 by 25, which is less or equal to 1, and same for the shaping. So x1 by 25 plus x2 by 20 plus x3 by 20, which is less or equal to 1. So here you can see for shaping, and for polishing you can say x1 by 40 plus x2 by 30 plus x3 by 40, which is less or equal to 1. We have total 1 hour only, so that's why all constraint is less or equal to 1. So see, this is the third constraint, and the last one is non-negativity condition, that is x1, x2, x3 all are greater than or equal to 0. So this is example number 3, which is slightly different from other example. Now we have fourth one. So up to this level we discuss all the problems usually regarding production. Now this is something different. This is personal management. So evening shift resident doctors in a government hospital work 5 consecutive days and have 2 consecutive days off. Their 5 days of work can start on any day of the week, and their schedule rotates indefinitely. The hospital requires the following minimum number of doctors to work on the given days. On Monday, they required minimum 35 doctors. On Sunday. On Monday, they require minimum 55 doctors. On Tuesday, they require minimum 60 doctors. On Wednesday, they require minimum 50 doctors. On Thursday they require minimum 60 doctors. On Friday they require minimum 50 doctors, and lastly on Saturday they require minimum 45 doctors. No more than 40 doctors can start their 5 working days on the same day. Formulate the problem as an LP model to minimize the number of doctors employed by the hospital. So here we have 7 days. So the decision variable is xj, that equal to number of doctors who started their duty on the day j, where j value of j is start from 1 2 3 up to 7 of the week. So that's why we need to minimize the number of doctors. So the objective function is minimize total number of doctors, that is z equal to x1 plus x2 plus x3 plus x4 plus x5 plus x6 plus x7, subject to the constraint. So let's talk about the Sunday. So a doctor who start his duty on Sunday, so that's which include in this, so that doctor will be present on Sunday, so that's why x1. But a doctor who start his duty on Monday, he won't present on Sunday, because all doctor have 5 consecutive working days and 2 week offs. Same for the doctor who start his duty on Tuesday. So that's why here we have x1, x1, x2 and x3 are excluded, and x4, x5 plus x6 plus x7, which is greater or equal to 35, because hospital needs minimum 35 doctors. This one is the minimum. This constraint is for Sunday. Now we can check for the Monday. So here same for doctors who started their duties on Tuesday and Wednesday, they will be absent on Monday. So that's why the second constraint is x1 plus x2 plus x5 plus x6 plus x7, which is greater or equal to 55. Minimum doctor requires on Monday is 55. So same for the third one. So this is for Tuesday, x1 plus x2 plus x3 plus x6 plus x7, which is greater or equal to 60. x1 plus x2 plus x3 plus x4 plus x7, which is greater or equal to 50. This is for Wednesday. x1 plus x2 plus x3 plus x4 plus x5, which is greater or equal to 60. This is for Thursday. This one is for Friday, that is x2 plus x3 plus x4 plus x5 plus x6, greater or equal to 50. And last constraint is for Saturday, x3 plus x4 plus x5 plus x6 plus x7, which is greater or equal to 45. Now here they mention in the problem that no more than 40 doctors can start their 5 working days on the same day. That's why all xj are less or equal to 40, where j running from 1 to up to 7, and those xj represent non-zero quantity. That's why xj greater or equal to 0 for all j. So this is all about how to formulate LP model. As we all know, model formulation is an art, and you can improve this by practicing. So to master on this art, you need more practice. Thank you.